Welcome back to our deep dive into the amazing world of math. You know how this works. We take some everyday thing and we try to really understand the math behind it.
Exactly. It's like peeking behind the curtain to see all the gears turning.
And today's topic is going to make you hungry. The math of deep fat frying potato snacks.
Oh, yeah. This is a good one. I love potato snacks.
Me too. But I bet most people don't realize how much complex math is going on every time they take a bite.
Right. It's not just about tossing something in hot oil. There's a lot of science and engineering involved.
So we've got some great sources to help us out. Wikipedia articles on deep frying and fluid dynamics, and even a research paper that tries to mathematically model this whole process.
Very cool. And what's the big question we're trying to answer today? What are we deep diving into?
The big question is, can we predict the exact moment a snack becomes buoyant enough to lift off from the fryer? They call it the liftoff time.
Ah, interesting. So it's not just about the snack getting lighter as it cooks.
Right. It turns out there's something else going on that plays a huge role. A vapor blanket that forms underneath the snack.
A vapor blanket. Okay, I'm picturing a tiny potato chip wrapped in a little sauna towel. What's going on there?
I know, it sounds a bit strange. But the research paper actually uses a multi-phase approach to model this process, which means they're taking into account the fact that the snack isn't just one uniform thing. It has different regions with different compositions of dough water and water vapor.
So it's not like a solid block of potato. It's changing and evolving as it cooks.
Exactly. And this multi-phase approach is important because it allows the model to capture those changes, like the formation and expansion of that vapor blanket.
I'm starting to see why this is so interesting. It's not just about heat transfer, it's about phase transitions and how the snack itself is transforming.
Absolutely. So
Yeah.
how does this vapor blanket actually form? What's the molecular level drama happening here?
Well, picture this. The snack hits the hot oil and immediately heat starts flowing from the oil to the snack.
Like dipping your toe into a hot bath. The heat wants to even out.
Exactly. And because the dough contains water and starch, that water starts to heat up. Eventually, it reaches its boiling point and starts to evaporate.
Turning into steam. But it's trapped under the snack, right?
You got it.
Yeah.
That trapped steam forms the vapor blanket. Now, here's where it gets really interesting. Water vapor, or steam, is way less dense than the surrounding oil. So as this vapor blanket grows, it's like a tiny hot air balloon forming under the snack.
Okay. So it's not just that the snack is getting lighter. It's also getting this extra lift from the vapor blanket.
Right. And the bigger the vapor blanket gets, the more buoyant the snack becomes.
I'm starting to see how this could affect liftoff time. But how do they actually measure and predict all of this?
That's where the math comes in. The researchers used a bunch of equations to model the complex interplay of temperature, fluid flow, and pressure, both inside the snack and in the surrounding oil.
I gotta admit, I'm not a math whiz, so I'm glad you're here to break this down for us.
No worries. It's all about understanding the basic principles. And even if you don't follow all the equations, you can still appreciate the elegance of how it all works together.
I'm definitely intrigued. But tell me, are we talking about simple equations here or something more on the advanced side?
Some of the equations involved are pretty sophisticated, like the Navier-Stokes equations, which describe the movement of fluids. Those are notoriously tricky. But the researchers were able to use some clever mathematical techniques to make them more manageable.
So they found ways to simplify the math without sacrificing accuracy. That's pretty impressive.
It is, and this is where the power of mathematical modeling really shines. It allows us to take a complex, real-world phenomenon and break it down into manageable chunks.
Okay, I'm following you so
Sure.
far. But how did they actually use these equations to predict liftoff time? That's where we're ultimately interested in, right?
Exactly. And that brings us to one of the most exciting parts of this research, the model's ability to predict the snack's density over time.
Right, so density is key here.
Okay.
And we know the snack is getting less dense as the water evaporates. But how do they factor in the vapor blanket? It's not like it has a fixed weight or anything.
That's the beauty of the model. It actually accounts for the changing volume and density of the vapor blanket as it grows and interacts with the oil around it.
So it's a dynamic system. The vapor blanket is constantly changing as the snack cooks.
Exactly. And the liftoff time is then determined as the moment when the snack's overall density becomes less than the density of the oil. That's when buoyancy takes over and the snack starts to float.
So we've got this complex dance of density changes happening inside the fryer.
Yeah.
And it's all being captured by these mathematical equations.
It really is. And what's even more remarkable is that when the researchers compared their model's predictions to actual observations, they found a very close match.
So they were actually able to predict liftoff time based on this model.
Yes, it's pretty incredible when you think about it. They took this complex process and boiled it down to a set of equations that could accurately predict what would happen.
That's the power of math,
Yeah,
right?
absolutely. And this is just the beginning. There's so much more to explore in this world of deep fat frying.
I can't wait to dive deeper. But for now, I'm definitely craving some potato snacks.
Me too. There's so much more to explore in this world of deep fat frying. Like, what happens after that initial heat transfer? What are the different stages of the frying process?
Yeah, I'm curious about that too. It can't just be a straight shot from raw dough to crispy snack. There must be some interesting transformations along the way.
You're absolutely right. The researchers identified several distinct phases, each with its own unique characteristics.
Okay, so walk me through these phases. What's the first step in this potato chip journey?
Well, we've already talked about that initial contact with the hot oil. That's what we call the heating period.
Right, the hot bath analogy you used.
Exactly. It's all about conduction, heat flowing from the oil to the snack, trying to even out the temperature.
So what's happening mathematically during this phase? Is it as simple as just waiting for the snack to heat up?
It might sound simple, but there's some interesting math going on here. We can actually model this process using something called the heat equation, which describes how heat spreads through a material over time.
Okay, the heat equation, I'm sensing some serious calculus here.
There is some calculus involved, but don't worry. We don't need to get into the nitty-gritty details.
As long as I don't have to solve any partial differential equations, I'm
Yeah.
good. But tell me, are there any visible changes happening to the snack during this heating period?
Not really. It's mostly a behind-the-scenes warm-up act, but something crucial is happening inside the snack. As the temperature rises, it gets closer and closer to the boiling point of water.
Ah, right, because the dough is mostly water.
Exactly. And that's where things start to get really interesting.
So the heat is building, the water molecules are getting all agitated, and we're about to see some action.
Exactly. Once the outer layer of that snack hits the boiling point, the water molecules start to break free and turn into vapor. This is the beginning of what we call the bubble inflation phase.
Okay, now we're talking. I can picture those tiny bubbles erupting all over the snack.
It's like a microscopic volcano.
So what's the math behind this eruption?
Well, now we're not just dealing with heat transfer anymore. We've got phase transitions happening, liquid water turning into vapor, and the equations get a bit more complex. We need to consider things like the rate of evaporation, the vapor pressure, and how that vapor blanket is expanding against the oil.
So it's like a tug of war between the expanding vapor and the resisting oil.
Right, and that tug of war determines the size and shape of the vapor blanket.
Okay, so the vapor blanket keeps growing, but it can't grow forever, right? There must be some limit.
You're right. Eventually, the bubble inflation reaches a point of equilibrium, and we enter the next phase, the quasi-steady state.
Quasi-steady. That's a mouthful.
It basically means things have calmed down a bit. The overall size of that vapor blanket is pretty much constant, but there's still a lot of activity happening inside.
So it's like a dynamic equilibrium.
Yeah.
A balance between the forces at play.
Exactly. And this quasi-steady state is actually super helpful for us mathematically.
How so?
Well, it allows us to make some simplifying assumptions, which means we can use those analytical solutions we talked about earlier to get some insights into what's going on.
Ah, so this is where the math becomes more manageable.
Right. For example, the model reveals that the shape of the vapor blanket at the bottom of the snack resembles a parabola.
Parabolas, those classic curved shapes. Who knew they were hiding in our deep fryers?
It's amazing how these mathematical patterns show up in so many unexpected places, but even though the vapor blanket might seem stable during this phase, the story isn't over yet.
There's more. I thought we were reaching the crispy climax.
There's one more crucial act to this play. While the vapor blanket might be chilling out, the evaporation fronts within the snack are still moving inward.
Okay, so the drama continues beneath the surface.
And that leads us to the final transformation, the one that gives us that satisfying crunch. And that leads us to the final transformation, the one that gives us that satisfying crunch. As the last bits of water evaporate, the snack doesn't shrivel up. It actually undergoes a crucial change.
So even though the vapor blanket is gone, the snack itself has transformed. What's happening at this stage? Is it just drying out, or is there something more going on?
There's a fascinating chemical process happening alongside all the physics. We've talked a lot about the water, but remember, the dough also contains starch. As the snack gets hotter, those starch molecules start to gelatinize.
Gelatinize. Does that mean they turn into gelatin, like the stuff in Jell-O?
Not quite. It's a little bit more complicated. Gelatinization in this context means that the starch molecules are absorbing water, swelling up, and forming a network.
Okay, so they're not turning into Jell-O, but they are creating a structure.
Exactly. And as the water keeps evaporating, that gelatinized starch solidifies, giving the snack its crispy texture.
Ah, so that's the secret to the crunch. It's not just about removing water, it's about transforming the starch.
Precisely. And that's why the snack doesn't just collapse once the vapor blanket is gone. That solidified starch provides the structural support.
I see. So there's a real balance here. If you don't cook it long enough, it'll be soggy. But if you cook it too long, it'll be brittle.
Right. It's all about finding that sweet spot where the starch is perfectly gelatinized and the water content is just right.
So the perfect potato snack is a masterpiece of timing and temperature.
It really is. And it's all thanks to the amazing interplay of physics, chemistry, and of course, math.
I'll never look at a potato snack the same way again. It's like a tiny little science experiment happening right there in the fryer.
And the cool thing is we can actually use math to understand and even predict how that experiment will turn out.
That's what I love about these deep dives. We take something seemingly ordinary and uncover this whole world of hidden complexity.
And it reminds us that math is everywhere, even in our favorite snacks.
Absolutely. Well, thanks for joining us on this delicious mathematical journey.
Yeah.
I don't know about you, but I'm suddenly craving some potato snacks.
Me too. Let's go get some.
We'll see you next time for another deep dive into the fascinating world of math.